Hey, welcome to Unit 1, Section 8, Linear Combinations. So in this lesson, we're going to be learning to write a vector as a linear combination of two other vectors. And so basically, the way this works is as follows. I've just got a little visual I've drawn over here. So if we have two vectors, and we'll just call them, and for now, we'll just call them, we'll call them U, and we'll call them V. And feel free to take down this diagram if you want, although we're going to use most of the space here for these examples. So you might want to just put this on another piece of paper or somewhere handy. Okay, so if we have vectors U and V, and we want to write the vector that would end at A or B, or C, what we can do is kind of like scale U and V and add them up. So let's think for a moment how we could do this. Let's say we want to get to A. We want the vector O. Okay, we want OA. And so in other words, we want a vector that kind of would represent going from the origin to A. Well, what we could do is we could travel along V some distance, right? Until we get to a point that we could travel to A from, that would be parallel, so that we could go along U a certain distance, right? So if we kind of came, say, to about right here, right, then we could then use part of U to get to A, right? And I'll just draw that. So this is going to be rough, but approximately here, right? Now, so let's call that. We'll call that this little guy right here. A times vector U, right? The red one. And really, we only came part of the way down V to get there, right? So this we'll call B times vector V. Now we know that, right, A and B in this case are going to be less than 1, right? Because we're actually just kind of scaling down vectors, U and V in order to get to A. And the resultant, of course, of adding these two, of A times vector U plus B times vector V would be the vector OA, right? This would be the vector from, and we'll just use gray here, right, from here to A. So, well, how could we get to vector, or to point B? Let's say we wanted to kind of figure out how to come up with OB. Well, it's the same idea, right? What we could do this time is maybe we could kind of travel backward along vector U. So we could actually use a negative, right? We could use a negative version or a negative coefficient so that we reverse the direction of U and use just enough of U, right? So that we can get to B along vector V, right? So we could come, say, out to here, roughly to there, and then we could travel along V, parallel to V, of course, right? Use part of V to get to B, right? And so this would just be another coefficient that we'd be multiplying U by in order to get here. And then we would be using, another coefficient on V to get there, right? So in other words, what we're really doing is just kind of taking parts of each of these vectors and then adding those parts in order to get to a point. And you can do this to get to any point you want to. Hopefully, this is a good illustration of that. So if we go back over here for a moment, what we'll do next is try example 1. So example 1 says, given the vectors U and V, express the vector W as a linear combination of U and V. And what we're going to do here is an algebraic version of what we did over on the right. Now, I forgot to mention that one thing that's really important is that if the two vectors U and V are collinear, then this is impossible. Let me illustrate that over here just for a moment, right? So if U and V pointed, right, along the same line, let's say that v pointed this way, that v was the dotted line, right? Then we actually could never get off this line to get to C or to A or to B, right? Because there's no multiple of v or u that would ever take us off the line. Really, what we would have is only one dimension to play with. We can only go this way or this way. So whenever we do this, we have to just check for a moment to make sure that the two vectors, u and v, are not collinear. So how can we do that? Well, remember that if they are collinear, what that means is they're a multiple of one another, right? So we could say are, right, u and v collinear. So we just need to ask this, and we need to show that this is not true. Well, we can say, is u a multiple of v, right? Is u equal to k times vector v, right? Well, how can we determine this? Well, we could use an equation. We can actually just create a vector equation here, where we'll have u 3, 5, and we'll set that equal to k times 2, 6. So really what we have here is two equations, because we have some x values. 3 is supposed to be equal to k times 2, and 5 is supposed to be equal to k times 6, right? Because we know that 3, 5 is equal to 2, right? 2 times k, 6 times k. So in other words, our first equation is 3 equals 2k, right? And our second equation is 5 equals 6 times k. So is there a k such that, a value of k that would satisfy both of these equations, right? Well, let's solve them, right? We have one variable in both of them, so really here k is equal to, pardon me, let's erase that. There we go. K is equal to 3 over 2. But here, k is equal to 5 over 6. And so because these k's are different, what that means is that these two vectors are not collinear, because there is no multiple of v that could equal u. Okay? So we can write not collinear. All right, so we checked that. Now, by the way, you could kind of eyeball this. You don't have to do all this math, right? If you have a look at u and say, shoot, can I multiply u by anything such that I could get v, right? So, I mean, to multiply 3 and get 2, we'd have to multiply that by 2/3, right? But if we do the same thing with 5, we're not going to get 6, right? So it's quite clear that they are not collinear. And you could just say something like, not collinear because u, right, vector u is not equal to a multiple of v. Okay, so you could just do that, and I would be happy with that. All right, so now to actually get into the business of this question here, what we have to do is begin with a let statement to create a linear combination. So we're going to let vector w, equal a times vector u plus b times vector v. And so what this means is we've got vector w is 1, 2, and a times vector u, which is 3, 5, plus b times 2, 6. All right, and again, here we have two equations, right? We actually have two coordinates. We have x and y in each term. So we can split this into two equations. We can say that 1 is equal to a times 3, so 3a, plus the x values here, which is plus 2 times b. And we can say that 2 is equal to 5 times a plus 6 times b. And that's our equation number 2. Okay, and now we're in grade 10 all of a sudden, because we have a system of equations in 2 variables, and we can solve this, right, using any of our strategies from before, elimination or substitution. Now, of course, when you have all these coefficients, right, elimination is nice and easy. What we could do is multiply row 1, 3 times row 1, and we'll subtract row 2. You could also put this into a little matrix if you wanted, if you haven't had enough Gauss-Jordan elimination by now. Okay, so 3 times 1 minus 2. Well, we would have, in this case, we'd have 3 times 3 minus 2, so we'd have 1, right? And that would be equal to, so now we'd have 3 times 3a, so that's 9a, minus 5, which is 4a. And of course, we know that these terms are going to cancel out because we set up the elimination that way. So a is equal to 1/4. All right, let's use this, and we'll use this to figure out b. Well, we know that 1 is equal to 3 times a, right, which we know is 1/4 plus 2b, right? So that was equation 1 that we just used. So we get 1 equals 3/4 plus 2b. And we can subtract that 3/4 from both sides. That gives us 1/4 over here is equal to 2b. And then we divide both sides by 2, and we get b equals 1/8. Okay, and so what we've actually done here is just come up with 2 coefficients. In other words, we need 1/4 of u, right? We need 1/4 of u, and we're going to add that to 1/8 of b, and that's what would give us vector w. So let's state this. So we can say therefore, okay, vector w is equal to 1/4 times vector u. Oops, not vector a. Vector u plus 1/8 vector v. And we'll draw a box on that to make it look nice and pretty. All right, let's look at example 2. So example 2 is like the 3-dimensional version of example 1. So we have 3 vectors, u, v, and w. Express u as a linear combination of v and w. So right away, we got to say, is it possible that v and w are collinear, right? Well, if we look at v and w, it's clear that there's nothing we can multiply 0 by to get 2, right? So clearly, we can say v is not equal to a multiple of w. Okay, and that's going to be true whenever you have a 0 in one coordinate but not the other. But certainly, even if we didn't have like say we had a 1 there, right? Oh, we could double a 1 to get 2, but then when we come to 2, we would have to double 2, and we'd have to see a 4 over here, right? And then 6 would have to mean we have a 12, right? So literally, all the components are proportional, right? And that's the key. All right, so they are not collinear. So what we can do then is go ahead and say let u equal a times vector v plus b times vector w. Okay, and so u is 1, -1, 1. And it'll be a times 0, 2, 6, and plus b times 2, -3, -1. Okay. All right. And again, we have 3 equations here, right? Actually, let me illustrate this a little bit better. Perhaps that you're a bit confused about how we were able to do this last time. So let's simplify. So if we know that, we can just leave this one on the left, but we can of course incorporate a and b into each of these vectors. We have 0 times a, which is 0. Then we have 2a, and then we have 6a, and we can add that to 2b, comma minus 3b, comma minus b, right? And then in the next step, we can take these 2 vectors here on the right side and just add them, right? So we would know that, well, we would add their components. We can go 0, the x value here, we can add the 0 to the 2b, and we would get, well, we would get just 2b because that's 0. And then for the y component, we would get 2a minus 3b. And the z component would be 6a minus b. Okay, so now what we've done is just kind of written this linear combination as one vector, right? So we have this position vector 2b, 2a minus 3b, 6a minus b, and it's kind of neat. This is in terms of the scalars, right, that are involved. So but since we have vector equals vector, it's true that x here must equal x here, y here must equal y here, and z must equal z. So this is why we can make multiple equations out of a vector equation. Basically, we're just equating the components. So 1 is equal to 2b, and that's equation 1. And then we would have minus 1 is equal to 2a minus 3b, equation 2. And finally, 1 is equal to, let's fix that, 1 is equal to 6a minus b, equation 3. Okay, well, this one clearly we can solve immediately because this is just b equals 1/2, right? So we can use this to eliminate b in both of these other equations. Let's just let's work with equation 3 for now. So we'll plug this in up here, and for equation 3, and we'll get 1 equals 6a minus 1/2, right? And so 1 is equal to, well, we could add 1/2 to both sides, right? And we get 3 over 2 on the left equals 6a, and divide both sides by 6. So we would get a equals 3 over 12, which is equal to 1/4. All right. Now the thing is, we actually had 3 equations here, right? Not just 2. And we've really only worked with 2 of them. We've worked with 1 and we've worked with 3. So what we need to do is we need to check 2 and make sure that A and B both work and satisfy this equation, right? Otherwise, this system would be inconsistent and we would have no answer. Okay, so let's do a little left side, right side check, right? Whenever you check an equation, you break it into 2 pieces. So we have left side is -1. And I'll just annotate what we're doing here first. So we're gonna check 2, right? Check 2. So left side is equal to -1. Right side is equal to 2 times a, right? Which we know is 1/4. So 2 times 1/4 minus 3 times, and so we know that b is 1/2, right? 1/2. Okay. And so what we're going to get is, well, 2 times 1/4 is 1/2. And this is minus 3/2. And we have, let's have common denominator already. That's nice. So we can go, well, we can go 1 minus 3. That's -2. So we're going to have -2 over 2, which is equal to -1, which equals left side. And so since these values satisfied equation 2 as well, what that means is that this system is consistent. There's an A and there's a B that works for all 3 equations, and therefore we can write this. We can say that vector u is equal to 1/4. That's our A. This is basically just going back here now, right, guys? 1/4 times v plus b, which is 1/2 times w. And this one is complete. Okay, coplanar vectors. So vectors that lie on the same plane in space are said to be coplanar. More specifically, vectors are coplanar if they lie on a plane when arranged tail to tail. So really, if you think about the xy plane, right? That's the plane, of course, that that would be like the tabletop plane in 3 dimensions, the flat one, right? So if you put any 2 vectors right inside that plane, they would be coplanar, right? And this is going to be true of any 2 vectors. No matter where you put them, you're always going to be able to kind of put them on a sheet of paper, right? You're going to be able to put a sheet of paper on the vectors so that you can cover them both. So this is the first idea. 2 vectors are always coplanar in any space, as long as they are not collinear. So if the 2 vectors are not collinear, they actually define a plane or form the basis for a plane. So we can use that later, especially in Unit 3. But for now, it's important to remember that coplanar vectors, 2 are always coplanar. So that brings us to the question of whether or not 3 are coplanar. And this is a problem in geometry we see. So this is how can we determine whether or not 3 vectors, given vectors, are coplanar? How can we show this? Well, pause the video here for a moment and think about this. Okay, so really, this just kind of brings us back to the skill we learned, right? If we have 3 vectors, if we look here for a moment, right, again, if we have 3 vectors, let's say A, the one OA and U and V, right, that are all in the same plane, then really you can write one of those vectors as a linear combination of the other 2. Right? And this would be true no matter how we shifted this paper. As soon as you take one of these 3 vectors and say point it in the 3rd dimension, right? We pull it out of the page, right? Now we can't use U and V to write a linear combination of OA, because if A is now is in some 3rd dimension, then we can't actually get off the page anymore, right? So really, this is only an issue when we're in 3 dimensions. So let's write these blanks. So if any one of the 3 given non-collinear vectors can be expressed as a linear combination of the other 2, it follows that the 3 are coplanar. And in what situations could this not be possible, and why? How do things change when we add a 3rd dimension? Well, that's basically what we just talked about, right? As soon as you add the 3rd dimension, it's very likely that 3 random vectors are not coplanar. So let's actually see. We've got one last example here. What happens with example 3? So determine whether the vectors U, V, and W are coplanar. Okay, so what we need to do here is, first of all, check if U and V and W, let's see if any of these are collinear, because if we actually do have a pair of vectors here that are collinear, then really we only have 2 dimensions to work with. And we know automatically, right, that we actually have all 3 vectors in the same plane. Because remember, any 2 vectors are always coplanar. U, 1, 2, 3, 1, 2, 3. We actually have 1, 2, 3 for all our coordinates, right? But U and V have a difference here, right? U actually would be almost equal with V, except for this negative. And so because of that negative, well, we know that U is not -1 times V because all its coordinates would have to be negative. And U, is there a number we could multiply U by? Well, if we switch the signs, or if we switch it to positive, well, we would have to have a 3 is -2, right? So in other words, U times something cannot equal V and cannot equal W. So you got to check V and W. Well, V is 1, 2, 3, and here we have 1 minus 2, 3. So again, if you have the same components, then they all better be the same. Otherwise, they're not collinear. So we know that these are not collinear vectors. So we can state that U is not equal to K times V, which is not equal to J times W. All right, so 2 kind of arbitrary scalars there. And from that point forward, we can now define, either of these vectors as a linear combination of the other 2. We just have to know if it's possible to do that. And if it is, then they're coplanar. So we'll just let, in this case, we'll let U equal A times V plus B times W. All right, so U is minus 1, 2, 3, and A, so times 1, 2, 3, and finally plus B times 1 minus 2, 3. Okay. So we need to now, we could go through the whole process now of simplifying and equating, but really what you can do is kind of pick off all the x-coordinates. So we're going to have negative 1 is equal to 1 times A, okay, plus 1 times B. So we have A plus B, and that's equation 1. Then we have 2 is equal to 2 times A plus minus 2 times B. So that's minus B. That's equation 2. And we have 3 is equal to 3A plus 3B. Okay, so what can we do here to solve these equations? Well, what we could do, first of all, is what we could maybe do is simplify some of these, because as you can see, we have a common multiple here, right, in 2. So let's take number 2. Divide everything by 2, and we're going to get 1 equals A minus B, right? And if we divide each of these by 3, then we're going to get 1 equals A plus B, right? So here is our number 1, here's our 2, here's our 3. Let's look at these now as a system of equations, right? And of course, what we could do now is use some elimination, but what you're going to find is that we get a system that is inconsistent, because do you notice how number 1 says that A plus B is minus 1, right? But number 3 says that A plus B is positive 1, which is actually impossible, right? You can't have the same expression equal to two different things. The only way that'd be possible is if the actual variables were different, right? So let's just, for the sake of exercise here, to see what would happen if we didn't happen to catch this visually, right? Well, we could take, let me say, we could take 2 and 3 and add them, right? And the b's would then cancel. So we'll add 2 plus 3, right? And we would get, well, 2 on the left side, and then we would get 2a, right? And then our b's would cancel, and so we would get a equals 1. We could then go ahead and substitute that into either of the two to find b, right? So let's sub that into equation 1, right? So we'd have negative 1 equals well, a is 1, right? Plus b, and so b equals minus 2. All right, so basically we just got b equals minus 2 and a equals 1. So this needs to be true for all of these equations, right? So let's check, first of all, let's check equation 2. So we'll check 2. Well, we would have left side is equal to 1, right side is equal to a minus b. So this would be 1 minus negative 2, which is 3, right? And since we got a left side that was not equal to right side, right, not equal to left side, we can say immediately, okay, the system is inconsistent, and that means that there is no value of a or b that would work for this system. All right, so the system is inconsistent, and so therefore u, v, and w are not coplanar. Now, why is that? Well, remember, what we were trying to do is show that we could write one vector as a linear combination of the other two. And we were unable to do that, right? Because our algebra failed. There's no A and B that would allow us to do this. Now, incidentally, what doesn't matter which vectors you chose here for your equation, your initial vector equation, because if you can do it for one, you can do it for them all, right? There's always going to be a way to write any two as a linear combination of another, if one of them exists. So basically, we have finished this example, and there are 5 questions there, page 340. Good luck with those, and we'll see you on the flippity.